Okay. So we continue the proof. So this is the second part. So the point of this is to look into um, the estimates and the techniques that we are going to do here. You see them in other places too. So for example, like weighting or making estimates for a product of things where you sort of give one term more contribution. So we're going to see that in this part. Okay. So going back, remember that we used v as a test function and substituted it in the equation that we have that we've obtained by subtracting two equations. So we have something like this. So what we're gonna do is we're gonna provide estimates for each of these terms. Okay. So the goal, remember, the point of this theorem is we need gradient estimates on U. So at this point, what we're gonna um, get is some kind of a gradient estimate on V. So together with some results on comparison with A-harmonic functions, this gives us sort of the gradient estimate on U. But not quite the form that we want. So remember we want something like term here with grad U squared, some power of R to the n minus 2 plus 2 alpha plus other things. So what I'm saying here is that with the things that we're gonna do here, we're gonna obtain some kind of a gradient estimate for this, but this power of R is still like missing. So this is some kind of an intermediate step, but the techniques are still very important. Okay? So again, goal is, or the plan is, estimate each of these terms, get a gradient estimate on V, together with results on comparison with A-harmonic functions, we get a gradient estimate on U, but not quite the form that we want, because we want something like this: grad U squared bounded by a bunch of constants and data times this power of R. Okay. So let us start with the first one. So I hope this doesn't take too long. Okay. So for the first one, let's look at, so we have integral over br of x0, a of x0, grad v dot grad v. Now this is where we're going to use uniform ellipticity. So remember that we have this direction, a of x is greater than or equal to little lambda of I, and what that means is that a of x, any vector, let's call it b, vector b greater than or equal to little lambda Euclidean norm of b squared, something like this. Okay, and this holds true for every x. So in particular, it also holds true for x equals x0. Okay, so using this, so note that grad v is a vector. So using this, what we have is this is going to be greater than or equal to little lambda. You have your grad v squared br of x0. So very straightforward. So this is why ellipticity is important, because these terms are going to be bounded above by a bunch of other things, like with terms like f and c and stuff like that. And if you have that, then so what that means is you can control this term. So any control that you have on this term gets passed on as control on grad v, okay, by the ellipticity condition. Okay, that's why it's important. And there are PDEs for which little lambda is not positive, it's 0. So you cannot make this. So the study of that is entirely different, I think. Okay. So anyway, I digress. Okay, so by uniform ellipticity, we get this. So this is fairly standard and you see it all the time. So next one is, let us estimate this term. So we have integral, let's zoom it a little bit, over BR of x0 of FV. So what I'm doing at this point is I'm just gonna make estimates for each of these terms, okay? Okay, so what is the straightforward thing to do? So the straightforward thing to do when you're estimating the integral of a product, you use Hölder's inequality. Okay, another thing here is, so on one side, we would have like grad V, terms with grad V. So the goal is to sort of make grad V appear in this side here so that we can put it or combine it with this grad V later on. So we're gonna demonstrate that later. But my point here is, it would be nice if we can estimate this with something involving grad V, because terms with grad V can be combined with this term here. Okay. So how do we make that appear? Okay, so let's see. So we're going to use Hölder inequality. Note that, okay, so let's see. The natural thing is, well, F is in LQ. Let's do Hölder inequality with Q and Q prime. But what we're gonna do here is, I'm gonna estimate this not with LQ, but with, so this is less than or equal to, I have integral of f raised to 2 star Hölder conjugate over the ball raised to 1 over 2 star Hölder conjugate multiplied to, I have v to 2 star 1 over 2 star b of x0. So remember that 2 star is the Sobolev exponent, and that 1 over 2 star is equal to 1 over 2, p is equal to 2, minus 1 over n. Okay, so we've seen this before. And the reason that we're doing this is because, remember what I said earlier, we need to make grad v appear on this side, so that we can combine it to some other grad v on the other side of our inequality. Okay. And doing Hölder inequality with this Sobolev exponent allows us to use a Sobolev inequality. In particular, I know that I can control this by some constant dependent on n times the L2 norm of the gradient of v. So this is true. Raised to 1/2. This is by Sobolev inequality. Okay? So again, let's recap. It's natural to use Hölder inequality with LQ and LQ prime because by hypothesis, F is in LQ. But the reason that we're using 2 star and 2 star conjugate is because if this is 2 star, it's sort of like straightforward to control it with the L2 norm of gradient of V using the Sobolev inequality. And we want this so that this can be combined with this later on. Okay. Okay. So what I'm gonna do next is I'm just gonna write this. How much space do I have? Okay. I'm just gonna write this in terms of n. So this is integral of f raised to 2n over n plus 2. So this is just straightforward calculation what the Hölder exponent of the Sobolev exponent is. Okay? This is just from real analysis. Raised to the reciprocal of this, so that's n plus 2 over 2n multiplied to You have v raised to 2n over n minus 2, which is 2 star, raised to n minus 2 over 2n. So this is the thing that can be controlled by this term here. So let's just put that in. So this is less than or equal to some constant dependent on n. Just going to copy them so that it's faster. Copy, paste, make it a bit smaller. And then let's just copy this. Copy, paste, let's change the color. Okay. So far, what do we have? We have that we can control this term by a constant just dependent on n, not dependent on v, times the product of this times this one, which is sort of what we want because we want this to appear so that we can move it to the other side. Okay, but note that it doesn't occur by itself. It's multiplied by this thing. So the next thing that I'm gonna do is also a fairly standard trick. I am going to separate this product using Cauchy's inequality, but with a twist, because remember that Cauchy's inequality says that for a and b greater than or equal to 0, you have ab is less than or equal to a squared over 2 plus b squared over 2. And there is this is just Young's inequality for p equals 2. So this is the usual one. But there is another form where given a positive epsilon, you can control this by epsilon a squared plus some constant that grows larger as epsilon grows smaller, b squared. So what is happening here? I can sort of control which term gives more contribution. So if I want a to have less contribution, I sort of pair it with a smaller epsilon. So this would be smaller at the expense of b having a larger contribution, of this term being bigger. So remember what we said before in the last video. In analysis, you see a lot of these things. You don't get things for free. So if you sort of want some kind of a result or some kind of a nice inequality or something like that, you sort of need to like give something up, to pay something, in order to get what you want, in order to like tip the scales to your favor. So like in this case, if I want this to be small, that's at the cost of this being big. Okay, so we're gonna apply that to this one, to the one that we have here. So for some epsilon 1 to be determined later, okay, so this is going to be less than or equal to epsilon 1 grad v squared. Note that this term is multiplied, is raised to 1/2, and then you square it by Cauchy's inequality, so the 1/2 disappears. And then you have here a constant dependent on epsilon 1 and n times this term squared. So you have integral over the ball. You have f raised to 2n over n plus 2 over n, where epsilon 1 positive to be determined, TBD later. And we're gonna see like why. Okay, it cannot be just anything. Okay, so recap what happened. I want to estimate this term. It's natural to do Hölder inequality, and at first glance it's natural to do like Hölder inequality with LQ prime, because you know that f is an LQ, but we want grad v to appear, so that's why we're applying Hölder inequality with 2 star instead. Because if you do that, then this term here can be estimated using the L2 norm of the gradient of v, which is what you want to appear. And that happens because of the Sobolev inequality. And then we separate those two using Cauchy's inequality with epsilon, meaning to say we sort of weigh things. We make this small at the expense of something being large. And we want this small later on because when we move it to some side, we kind of want that term to be positive. Okay. So we more or less sort of do something similar for the other terms. So let's see. So the other term that to be estimated is, so I have absolute value integral over BR x0 of CUV. So we have here a product of three things. So again, this is going to be a Hölder inequality sort of thing. So we already know that we are going to use Hölder inequality with V being in L2 star so that we can use the Sobolev inequality. We would also want U to be in L2. Note that U is in H1, so by Sobolev embeddings, it's going to be, remember from our preliminary video, Sobolev spaces gives you better integrability. But in this case, we just want it to be in L2 because later on in our estimates, we are gonna estimate things in terms of the H1 norm of U, and that is a combination of L2 norm of U and grad U. So we want L2 norm of U to appear. Okay. So if you have V in L2 star, U in L2, then if we want to use Hölder inequality, this sort of forces C to be in Ln. So this is why we need C to be in Ln. Because so that we can make the terms that we want to appear. So remember that the minimum assumption on C is that for the problem to make sense, it's in L of n over 2, but we're requiring something stronger, it's in Ln, and the reason is so that we can get the estimates that we want. So we're sort of kind of fudging the thing. I'm not quite sure whether there's going to be a counterexample if C is in Ln. So I don't know. But what I do know is that if C is in Ln, then we can show that U is in C alpha. If C is it's not in Ln, I do not know of a counterexample. Okay. So with these in mind, and you might be wondering, okay, Ryuji, how did you think of Ln? Just to get this, it's just 1 minus the reciprocals of these, okay? And that would give you 1 over n, okay? Okay, so with that in mind, we are going to use Hölder inequality. So this is less than or equal to C, Ln norm of C times L2 norm of U times L2 star norm of V. Okay. Now, of course, you can check, and of course, I kind of want to remind everyone that at any point you can like pause the video and try out the calculations yourself. That would be like a good way to like learn the material. Okay, so you can check that if you add these, it's equal to 1. Okay. So like what we said earlier, this is going to be estimated by some constant times the L2 norm of grad V, which is what we want. Okay. So this is less than or equal to C, some constant dependent on n. So this C is different from this C here. Okay. Okay, and then what? Yeah, my boyfriend tells me that when I talk about math, my Tagalog accent comes out. So I just noticed that I kind of rolled my R there. Okay, but anyway. So I have here this. Yeah, I do hope that uh, when you watch this video, you do the calculations together with me. It's more fun, it's more proactive. So, and that is sort of my goal for this YouTube channel, is that it's like a resource for grad students. So, yeah. Okay. So we have this. So what are we gonna do? Okay, so we're going to separate these. So we don't need to separate them, all of them separately. We just need to single out this term. So we can combine, we can apply Cauchy's inequality with this times this and separate out those two groups. Okay, so by Cauchy's inequality, this is going to be less than or equal to some epsilon 2 times this. So this is raised to 1/2, so you square it, the 1/2 disappears, plus some constant dependent on epsilon 2 and n, multiplied to, okay, 2 over m times the L2 norm of u. Okay, where epsilon 2 positive, PBD later. Okay, so at this point it's getting a bit messy. You have like a bunch of terms, a bunch of inequalities. So let's just recap what's happening, at least for this term. We want to estimate this term. What do? It's natural to do Hölder inequality because it's an integral of a product of things. So the question is, what exponents do you assign things to with? So I want grad v to appear, so I'm using the Sobolev exponent. I want grad u to appear because the estimates are in terms of h1 norm of u. So that sort of leaves us with, okay, c needs to be like in ln. Okay, so that's why we have these exponents here. Okay, next step is just applying the Sobolev inequality in order to estimate these terms in terms of grad v. And then we want to single this out. So we use Cauchy's inequality, but with some epsilon here to be determined later. Because when we combine things later on, we want them to be positive. Okay? Okay, fairly straightforward. Now let's look at the other one. So for the last term, I have something like this. So absolute value integral of, we have here a of x0 minus a of x grad u times grad v. So we want to estimate this one. So note that this here is a constant matrix. X0 is some fixed point. And this is an integral in x, so you have some dx here. Okay? So this is non-constant, this other one. Of course, these depend on x as well. Okay. So this is less than or equal to, put the absolute value inside, and the absolute value of this is less than or equal to, so you have some norm, some matrix norm of times norm of this, norm of that. Okay. Note that, what did I use here? I used the fact that the absolute value of the dot product of two vectors is less than or equal to the product of their magnitudes, and the magnitude of A matrix, some matrix A times a vector B is less than or equal to some matrix norm for A times the norm of B. Okay, fairly standard linear algebra stuff. Okay, so note that this term here will be controlled by the modulus of continuity of A. So this would be controlled by tau of the distance between x and x0, which is like tau of r. So note that x here is in this ball. So, and what that means is that the distance between x and x0 is at most r. Okay. So this term here is controlled by the modulus of continuity at r. Okay. So if r is small, meaning to say if x is close to this term is small. Okay. So let's write that down. This is less than or equal to some tau of r, grad of u, grad of v, br of x0. Okay, so what are we gonna do now? So at this point, we're not gonna use Hölder inequality because grad v appears already. Okay, so you might be wondering, well, I want to estimate a product of things. It's a product of things. I should use Hölder's inequality. But remember that we want estimates to be in terms of grad v, and grad v is already here. Remember that in the previous estimates, you used Hölder inequality in order to make the L2 star norm of v appear that you can control by the L2 norm of grad v using Sobolev inequality. But for this one, grad v already is there, so you just need to separate this from this. Okay, so we do that with Cauchy's inequality with epsilon. Okay, so I do hope that these sort of discussions make it more intuitive why we do these steps, because I kind of understand when I was first studying like estimates and PDEs, I was like, okay, I understand the steps, but the question is why? Like, how did you even think of this? But if you look into it a bit more closer, then you'll see that these steps are actually natural. Okay. So we're gonna separate them because we want a term with grad v, the L2 norm of grad v. Okay, so this is less than or equal to, let's put some epsilon 3 there. I have grad v squared, br of x0, plus some constant dependent on epsilon 3. No, this would get squared. So I have tau squared of r, grad u squared, br of x0. So note that this is just a function of r. It doesn't depend on x. I can take it out of the integral. So okay, so we have this one here. Okay, so we have an estimate for this. So let's recap what is going on, what is happening. Yeah, I've heard some people complain about this thing in analysis, like you sort of get lost in all the inequalities and everything. So it's good practice to like, okay, so what's happening? What is happening is with the estimates that we've made, I have a lower bound for this one using uniform ellipticity. And the work that we've done after that is estimating these terms. So I have some term here. So what I'm gonna do is the terms here with the L2 norm of v, I am going to put that here. Okay, so let's write that down. It's a lot, but let's see. I'm going to just copy things so it's faster. Let's copy this term here. So I hope this is not too dizzying. Okay, and let's shift things around. So I know that this is true, and that this term is equal to, okay, I'm gonna do it a bit slowly so it's not dizzying. I might edit it, we'll see. Okay, let's copy this. And then these terms are less than or equal to, okay, sorry about this, okay, could be a lot, oops, copy, okay, paste, plus copy, paste, plus, okay, last one, copy. Okay. So what do we have here? So from uniform ellipticity, excuse me, I know that this is going to be greater than or equal to this one. So, okay, so we have that part. This is equal to this. And I know that this is controlled by these terms. So the first one came from controlling this. The second one came from controlling this. And the last one came from estimates for the last term. Okay. Now, what do you notice? Well, I have here L2 norm squared of grad V, and those terms appear here as well. So what we're gonna do is we're gonna like move those terms to the other side. And so I can factor out this term, and I'll be left with something like lambda minus epsilon 1 minus epsilon 2 minus epsilon 3. Now we want that to be positive. So that, remember, the goal is to obtain a gradient estimate for V, so that you obtain a gradient estimate for U. Okay. So if that is negative or 0, when you divide, the inequality would reverse. That's why you want it to be positive, which you can do. So you can choose these to be small. So let's just note that. So you choose epsilon 1, 2, and 3 to be small enough such that lambda minus epsilon 1 minus epsilon 2 minus epsilon 3, this is positive. Okay, so doing that, so you move things and then you combine them, then divide by this term. What you get is, so the choice of these epsilons are dependent on lambda. Okay, so what you get eventually is this one. Okay, let's write that down. What you get is the L2 norm of grad V squared BR of x0 is less than or equal to some constant dependent on n, and the epsilons which are dependent on lambda, maybe some other things, I'm not sure. Okay, that multiplied to, okay, so what are the things left on the other side? So I have there tau squared of r, grad u squared, br of x0 plus n. So really, I'm just like listing down the things that are already here. So it's just a lot of writing. Kind of looks complicated, but not. It's not as daunting as it looks. n over m plus 2, I have br. Just a bunch of writing down. Okay, and I am calling this equation triangle. So this is equation triangle. Okay, so based on the techniques that we've used, we have achieved an intermediate goal, and that goal is to obtain a gradient estimate on the L2 norm of grad V. You might say, oh, Ryuji, this is not the L2 norm. Okay, well, this is the square of the L2 norm, which gets you like an estimate on the L2 norm. Okay, so recap what happened by a specific choice of test function, just by standard things, uniform ellipticity, Hölder inequality, Young's inequality, and some technical things like the Sobolev inequality, which aren't too difficult to apply, you get this estimate here. And a lot of analysis of PDEs is that, really. It's gonna be a bunch of Hölder inequality, Cauchy's inequality, triangle inequality. So fairly standard tools. So what I'm saying here is, if you're familiar with a handful of tools, you're gonna be fine. Okay, it kind of looks complicated, but really, if you take note of what each term actually is, it's fine. It's just long to write, but it really is not that complicated. Okay, so we have this term here. Now, remember, what is V? V here is U minus W. It's the difference between our solution U and W, which is a solution to a constant coefficient equation. So it's an A-harmonic function. Now, eventually, what we want is an estimate for U. So I am going to provide an auxiliary lemma that we're not going to prove. It's in Han and Lin's book. So the lemma is, so auxiliary lemma. The lemma is, excuse me. For any h1 function u, for any h1 function u, of course in h1 of the ball, of the bigger ball, excuse me, you have this estimate. And this is true for any. Okay. So this result gives us some kind. It's like a comparison result between h1 functions and the specific function w. So we have something like this. The proof of this is not too difficult. It's just a bunch of calculations. So that's why I didn't include it in this video, because as it is, it's already kind of long. But what is this saying? So we have two balls here. One, a smaller one of radius rho, and one, the bigger one of radius r. One is contained in the other one. And what this is saying here is that I can control the L2 norm in the smaller ball by the L2 norm of that thing, the gradient of u, in the bigger ball, times this thing here, which is the L2 norm of the gradient of the difference. And we have this factor here as well, so that for if rho is smaller, this loses contribution, sort of thing. So it's some kind of a technical lemma, and I think Han and Lin in their book calls it like a comparison between, or comparison with harmonic functions kind of lemma. Okay. Now in our case, this is V, and what we have so far is I know how to control this. I know how to estimate that. The estimate is this long thing here. Okay. So remember that our goal is to obtain some gradient estimate on U. What we have so far is a gradient estimate on V. So if I'm going to apply this lemma, this tells me that an estimate on U is a combination of this term here, uh, sort of weighted by how big this smaller ball is, times the estimate that we have for V that we know already. Okay. So, combining that, we now have this one. So, let's just copy this. Paste. Make it smaller. Okay. So note that what would happen, we would just have this additional term here. So this is going to be a different constant, but just a constant, so call it C. Just going to shift things around. So I have plus rho over R to the n. Okay, so we have this one, and that I call equation 1. Okay, so we now have attained the second intermediate goal, which is to obtain a gradient estimate for grad V. Okay. So what is the next step? So the next step, this is not supposed to be grad V, this is grad U, I'm sorry. Grad U. What is the next step? So remember, the goal is to obtain some gradient estimate on grad U, or gradient estimate on U, where the estimate is sort of weighted by a power of R. So here, that doesn't appear yet. So there are a bunch of major steps that we still need to do, okay? So first things first, let's just focus on this complicated looking thing here. So eventually I want, in order to produce a power of R, these terms must be multiplied by that power of R. Okay. So again, I want this to be estimated by a bunch of constants times R raised to n minus 2 plus 2 alpha. That's the goal. But at this point, that power doesn't appear yet. Okay, so we need to do some other things. And in fact, the third part of this video would be working on that. But at this point, we can say, we can sort of make that appear. So we focus on this term here. Note that we haven't used yet that F is in LQ. We just casually mentioned that LQ for Q in n over 2 to n would imply that LQ is in L of 2n over n plus 2. Okay, of course, if the measure of the set is finite and everything, but we really haven't used Q yet. So what we're gonna do here is we are going to use that now in order to make that power of R appear. So this is another thing in analysis. We are requiring something stronger for F. It not being in the minimum space, which is L of 2n over n plus 2. We're requiring it to be in L2, which is something stronger. But because of that price that we pay, we would be able to make that power of R appear. Okay, so another common thing in analysis. Okay, so let's go on working with that. Okay, so we focus on this and we need to make that power of R appear. Okay. And in these calculations, we are also going to prove that for that particular Q, it follows that F is also in L of 2n over m plus 2, which we just like mentioned at the start of the proof, but we didn't really show. At least I was saying that to me, it wasn't obvious, so I'm gonna work on it. Okay, so how do we do that? Okay, so I have here f to 2n over m plus 2 dr of x0 raised to m plus 2 over n. Okay, so let's think. What is the natural thing to do? Okay, so the natural thing to do is, well, first let's ask, what do I want? Okay, I want a power of r to appear. So that can happen if I applied Hölder inequality to this times like 1, because that would force the measure of the ball to appear, and that the measure of the ball is a function of r. So that would force r to appear. Okay, that's promising. So we're gonna apply Hölder inequality to this function n1. Again, why? So that the measure of this ball would appear, and the measure is a function of r. Remember, we want r to appear. Okay, that's promising. So the question is, what exponents do you use? Well, what other information do you know at this point? Well, I know that f is in LQ. So is it possible to use Hölder inequality in order to make an LQ norm of f appear here? So you have f to the q integral, something like that. Okay, so to do that, this is gonna be less than or equal to. So if I want that to happen, I need to figure out what exponent should I raise this function to. Okay, so I have this function. So it's very straightforward. So I need to raise this to a power that would give me q. So first I just need to cancel out this and then multiply that by q. So the power that I'm looking at is, q m plus 2 over 2n. So that this would cancel out with that. I'm left with just q. Okay. Raised to the reciprocal of this one here. So I have 2n over q n plus 2. And remember that this term is raised to this power, so we need to include that as well. Oh, let's make this red because that's like the new term. Multiplied 2 n plus 2 over n. Okay. Multiplied 2. So you just have like 1 raised to the conjugate of this one, so that's just 1. What you're left with, this is the measure of the ball raised to the reciprocal of the conjugate of this. So it's 1 minus this times this. Okay. So let's write that down. I have 1 minus 2n over q n plus 2 times n plus 2 over n. I just want to share that when I was doing this earlier, I spent a lot of time because I couldn't make things right. And the reason was I forgot this term. So sometimes it's very frustrating in math in general, like some missing terms just like mess everything up. Okay, but before we proceed, let's make sure first that this is an allowable exponent. Note that you can only use Hölder's inequality for pairs p and q for when p and q are greater than or equal to 1. They cannot be less than 1. So the question is, on the assumptions that we have on Q, is this greater than or equal to 1? Okay, so let us show that. I have the calculation here in my notes. So we want to show that Q m plus 2 over 2n is bigger than 1. Or equivalently, we want to show that Q is bigger than 2n over m plus 2. Okay, so this is easy. Okay, so indeed, so note that Q is in the interval n over 2 to n. So as Q is bigger than n over 2, it suffices to show that n over 2 is greater than or equal to 2n over m plus 2. Okay, so that's obvious. Okay, so n over 2 greater than or equal to 2n over m plus 2. This is equivalent to saying that you can cancel out n, so you have 1/2 greater than or equal to 2 over m plus 2, equivalent to 1/4 greater than or equal to 1 over m plus 2. What did I do? Just divided both sides by 2. This is equivalent to what? 4 less than or equal to m plus 2. So I took the reciprocal on both sides, so that reverses the inequality. So, okay, so what do we have here? This is true if and only if this is true. But this is true. Why? Because we are in the case where n is greater than or equal to 2. So in fact, so it's clear that m plus 2 is greater than or equal to 4. Okay, so that shows that this term is bigger than 1, so we can use it as an exponent in Hölder's inequality. Okay. Okay, so let's erase this so we have space. Do I want to erase it? Okay. I have space. So now let us focus on this term. So let's copy that. Copy, paste it here. So I want that power of r to appear. Okay, so let's see. So I know that this is equal to some constant times r to the n, and this is raised to, so that's multiplied to 1 minus 2n over q times m plus 2, m plus 2 over n. So can we cancel things at this point? Yes. So we have that. So this is equal to c times r raised to, what is this? This is just calculation. I have nq plus 2n minus 2n multiplied to n plus 2. So this cancels out. So I have c times r raised to nq over q, that's just n. Wait, there is something wrong here. I am sorry. This is supposed to be nq plus 2q. So 2q minus 2n. Okay. So we have nq over q, that's n. 2q over q, that is 2. Minus 2 n over q. Okay, so we are almost there. So remember, we want, what do we want? We want the exponent of r to be, so we want it to be of the form n minus 2 plus 2 alpha, where alpha is less than 1, greater than 0. So we're going to force this to appear. So I am going to write this as c r raised to n minus 2 plus 4 minus 2n over q. So in analysis, you see a lot of like these like sort of like cheats or whatever. So I'm just writing here 2 as negative 2 plus 4, so that I can write this as CR raised to n minus 2. I factor out 2 here. I'm left with 2 minus n over Q. And this term here, I'm calling that alpha. And note that if Q is in n over 2 to n, I'm leaving it to you to check that indeed alpha is in that magic interval 0, 1. Okay. It's also a nice exercise, like what if alpha is bigger than 1? What can you say about Hölder continuous functions for alpha bigger than 1? Okay, there is something like peculiar about it. That's why we're not considering alpha values bigger than 1. Okay, so we want them to be in this interval. Okay, so what happened? Okay, it is a lot. What happened? Let's backtrack a bit. We already have the gradient estimate for u. But what we want is gradient estimate of u times a bunch of things times the power of r. And that is a bit tricky to do. The easiest part is dealing with this, where we haven't used yet the fact that it's in LQ. Okay. So we did Hölder inequality and we made a bunch of calculations in order to make the LQ norm appear. And it's Hölder inequality because that would force the power of r to appear. Okay. So I also kind of want to point out, I forgot that. Let's write this down. So this is equal to just LQ norm of f multiplied to, so what cancels out? Note that this cancels out, that cancels out, 2 over q. And we have BR x0. We've already calculated, no, let's write, times constant r n minus 2 plus 2 alpha. Okay. So I kind of want to point out as well that if f is in LQ, then it's in L2 n over m plus 2, which we just mentioned earlier today. And this is the proof. Because if f is in LQ, this is finite, so this is finite. F is indeed in L of 2n over n plus 2. But again, reiterating, the reason that we want LQ instead of the minimal assumption, so that we can make this power of r appear. Okay. Okay, so with this estimate, we have, okay, let's just copy this because it's very long. And we're nearing the end of part 2. So we just need to replace this. We replace this with what? We replace this with r to the n minus 2 plus 2 alpha times the LQ norm of f. Push it all the way to b1 squared. So now we have this estimate. So we are sort of fairly closer to our goal of having the gradient estimate for u with like powers of r. Okay, so the next part, the third part, would be dealing with this term. Okay. So yeah, so that's it for part 2. So part 2 involves obtaining estimates and then just a demonstration of how it's natural to use Hölder inequality and Young's inequality in a lot of situations when you want to estimate intercross of products. Okay, so yeah.